we're given an arbitrary type tau and some value v of type tau, closed value. Okay. Then we know that E applied to tau v. In a language, what happens when this steps? In a language where all programs terminate, we know that this will always reduce in some number of steps to v. Right? The intuition being that this is a polymorphic function. You give it any arbitrary type tau, and then you give it a value of type tau, so the input. The only alpha that it can ever return to you is the input that it got. So evaluating this expression will always give you back the input. Right? In a language where, so this is a free theorem, you know, that E must behave like the polymorphic identity function. In a language where programs do not terminate, what sort of free theorem can we get? We can't say that this always reduces to a value v. Right, so either it reduces to a value v, or E tau v diverges. I'll write that for diverges, right? It doesn't terminate. Okay, so one of the things that I want to show you is, you know, once we take our unary logical relation and extend it to a binary one, I want to show you how one uses that setup to prove free theorems. The other interesting thing that we'll be able to do is, you know, as I was saying, prove the two implementations of an abstract data type are equivalent. So let's just write a very simple example. Okay, so something with, let me see. So suppose that tau is, here. What do I want to use? Okay. All right? I'm going to write down two expressions, and you tell me if they're equivalent. So E1, I want to write down two expressions of type tau, so two packs, right? All right, so I could create a pack where I use int for alpha, as the witness type for alpha, and now I want a pair here. So let me take, since alpha is int, I need to put an integer here, so I'll use 1. And now I need to put a function from int to bool. Okay, so I'll use x int, let's say x equals 0, where equals here means integer equality. Okay, and here's another one. This time I'll use bool as my witness type. Okay, and I'll use true for the alpha here, right, because I need a boolean. And then I need a function from a bool to a bool. In particular, right, let's do not x. Okay, so I have an E1 and an E2. Let's take a look at these. These two expressions are equivalent, no matter what context you put them into. Let's see why. Well, okay, what can you do with them? You can unpack them, right, and use them somehow, right? So basically the idea is that we want to treat, you know, under the assumption that int is related to a bool, and we want to treat 1 as related to true, like think about it as related inputs to related outputs. This function over here takes inputs of an abstract type alpha. All right? So here, the only alpha that I can give it will be the only alpha that I have, which is this 1. So this function can never be called with anything except for the thing sitting over here, right? So it will always be called with 1. So when we evaluate the function, it'll apply to 1. We'll be checking whether 1 is equal to 0, and we'll get false, right? So if you can ever call this function, if you can ever apply this function to anything, it'll always be this 1, and therefore the function will always return false. All right, let's look at what happens in this situation. Again, it's the same thing. We have a value of type alpha sitting over here. The function wants something of type alpha. So the only thing that we have in our hands, that we can get in our hands, that has, that satisfies the type alpha, is going to be this value true. So the only thing that we can ever apply this function to is true. So when we apply it to true, not of true is going to be false. So when we apply it, we'll always get back false. Right? So if you unpack these packs and you take out the first component and the second component, basically the only interesting thing you can ever do with it is take out the first component and take the second component and apply it to the first, right? Because otherwise you can't use this function in any other way, because you can never supply it with an alpha. Nothing else will type check. So basically these two packages are equivalent, no matter what context you plug them into. Right? And logical relations, the binary logical relations that we want to start setting up, give you a method for proving that. And for proving free theorems of this form. This is a rather baby trivial example of two implementations of an ADT. There are many, many more interesting ones, but the point is to show you the techniques to get you to be able to prove equivalence for the really interesting ones. Okay, so we'll start with that tomorrow, all right? We'll extend this to a binary setting.